Good evening, everybody. This is Dr. Schulman. I thought I'd make this last video. It's the last content one for the course. It's the ANOVA course or analysis of variance. Um, I hope you found these really interesting. The feedback that I got from a lot of people said these were really useful throughout the way. But if you want to see anything different, if you need help, don't feel free to reach out. Now, ANOVAs or analysis of variance, like everything we've been doing has been either one group in the population, two groups, so like proportions, like yes or no things. Um, we just did t-tests, which have two groups, which is cool. But now we're going to do analysis of variance. And analysis of variance basically just means we have three groups. And an analysis of variance gives you an F stat, an F statistic. It's just like a T statistic for means. It's just like a Z statistics for probability. But the F stat only finds a difference, like a difference there. We don't know if the difference between mean one and mean three, mean two and mean three, between mean one, mean two, and mean three. All we know is that there's some difference there. Now, if you can find significance for an ANOVA, you get to do what's called a post hoc. What's a post hoc test? That means it's like we know there's a difference. Now let's find it. Now, I've done these before in my own research. Because I might as well just show you one. Okay, let me show you. I wasn't planning on showing you mine, but I think just like as I'm talking about, I feel like it'd be good for you to see some of my own stuff. So why not share? So I'll show you what like I don't know what kind of looks like. If I can find one, if I can find one that I did in my research. I think I have the data in a training that I did. And let's see if I can find it. If I can't find it, I'll just start doing stuff, but I thought I might be able to. I've got my own research. I'm just looking through it, so obviously you can fast forward through this part, especially if right, I have my dissertation research. That's really long and boring. That's a mix between qualitative, which were interviews, and quantitative. All right. Mhm. Okay. Uh, done so many lectures. Sorry. Only I was more organized or thought I was going to do this right from the beginning. I'm going to look for maybe one or two more things. If I can't find it, I can't find it. I think I found it. Yes. Awesome. All right. So let me share my screen. So here's some of my own research that I did. This is actually like what got me into research. So teach a lot of high school math, and I was like trying to figure out like what is the best way to teach like high school mathematics. And I was really into relativistic teaching. So I was putting my students' names, their jobs, all their stuff, like their sports scores, as much information about them as I could into the math. But I had to test it against something. So I tested against historical teaching, which was like teaching students about where the math comes from, like who created it and why. And then I was also testing against traditional teaching, where I just straight problems, theoretically. And I'm going to share my screen so I can show you my results. I did an ANOVA. All right. So here's the results. Um, so these were my ends. So I was teaching what was called like an ACT prep course, the math and science versions. And I varied what periods I taught these groups. So for one semester, MHT, like the historical teaching was like second period, and then for one semester it was like eighth period. So I varied them, but I did this for a whole year. So 38 ended up being the historical teaching, 42 were in the relativistic teaching, which was I thought would be the best, and traditional teaching was here. And it turned out the thing that I thought was going to be the best was the worst. Great, right? So I gave them all the same tests at the end. And I gave them the same sorts of problems. The only thing I did was change the intros. So for the historical teaching, if it was a geometry thing, I'd be like, this is Pythagoras. He was a crazy guy who killed people and was afraid of frijoles and like all this crazy stuff about Pythagoras. And like, but this is why he created the Pythagorean theorem, and this is why it's important. So I just taught them about like where the math comes from and where it is. So that's the historical teaching. Traditional teaching, I said it was just straight. Here's the formula, here are the problems, and then relativistic teaching. So I basically got these values. This was just the scores on the final, right? The final was just the standard practice ACT test. Historical teaching scored 80. The relativistic teaching scored about 68, and the traditional teaching scored 71. Now, we could say, oh, they're different, right? Like, ooh, but like I had to use stats to kind of prove that they're different. Like my whole job was to prove that these were actually significantly different. 68 and 71 seem pretty close, right? So these are the means. So that was the scores on that final exam they had, which was the practice ACT. All took the same one. This was the value squared. These were the standard deviations. Notice that the relativistic had the biggest range. The historical teaching had the smallest range. So they also kind of scored this game. Now I also found out, I also like had pre-data that showed that like I had some really smart kids in the historical teaching class, and I did some other analysis to like make sure that was like balanced out, like to make sure these groups were actually equal. And the fact that I varied the periods, and there was like two full separate classes of each made me feel confident about the results. But I did a bunch of other stuff just to make sure the data was good, like that this was a general sample to use. So to do an ANOVA, you need your sum of squares between. So we have to find the differences between each of the treatments. That's what this is. Degrees of freedom. We have three groups. So -2 is -1. So 3 minus 1 is 2. And that's the mean squared. That's all the mean squared. The within treatment. So basically what an ANOVA does, it takes all the betweens, all the withins, and kind of like figures out a value. So we're figuring out the differences between each groups, and we're also figuring out the variation within each group. When we put all that together, we get an F statistic. There's our F statistic, 4.595. And I used a 0.05 level. And my P value, I ended up with 0.01. Isn't that great? So I was like, wow, I'm like 98.8% sure this is not due to chance. So I was like, wow, I really have something here. And I used historical teaching to kind of like build my whole dissertation research. I know, kind of wild. But once I found the difference, I wasn't sure where the real difference was. So this is where you have to do what's called a post hoc analysis. The post hoc analysis is something like this. So this is your two key. I'm going to see two keys, but the post hoc analysis, see how it relates multicultural historical teaching, multicultural relevance teaching, and traditional teaching. And it gives you significant values right here. Now you can, and we also have the confidence interval too. So basically, you can see that the only real difference is where between historical teaching and relativistic teaching. That relativistic teaching is just significantly worse than historical teaching. That historical teaching is really worse than relativistic teaching. This is the only one with the stars. The means are different enough. I can't say anything about traditional teaching. So the only like real thing I can say with my data is that relativistic teaching, putting students' names, jobs, um, and sports scores in the assignments in like the introductions was worse than teaching students about where the math came from and who created it and why they created it. That's the only piece of like real stats I can pull from my data. Now this is the effect size, and we've talked about effect size before. I mentioned it before, but as long as I'm over 6%, I can say I've got a medium effect size, which means I can generalize this to other groups. That's what that means. So that's the data here. Oh, this is like a big difference about the both. So historical teaching, I incorporated reading, writing, history, and math. They were hands-on sorts of experiments. I used role models from the past and the present. I also used current news articles. So my historical teaching actually had like people presently using it too. So it wasn't just the past, it actually had jobs for the future and things like that. And for the relativistic teaching or relevant teaching, I put their jobs in, they acted as change. I used cultural references. I let their interests guide the instruction. So that's the main difference between these two ideas. Why do I think the relativistic teaching was worse? I think the students saw themselves in the math so much, they're like, I already know how to do it. So that was a little bit about ANOVA using a real life example that I did and I presented at a conference, which was really cool. And these were, and just, but this isn't enough, right? So if you do an ANOVA and you get your data, it's just not going to be enough. What do I mean by that? You always have to go an extra step. I know that there's a difference here. Where is that difference? That's where the two key comes in. And I just know between this one and this one, between this one and this one, that's it. So I hope that was an interesting introduction for everybody. I'm going to be doing the numbers into intro statistics, 11.3. We've got chi-square in this, as well as ANOVAs, or analysis of variance. When somebody says ANOVA, they're just saying analysis of variance. Now, there can be MANOVAs, which is a multiple analysis of variance. You can do a bunch of stuff. But for our ANOVAs, when they say this word ANOVA, they mean what? Analysis of variance? Basically, and we'll go through the book and everything else, but your null hypothesis is just this, that ready? Mean 1 equals mean 2 equals mean 3. And your alternative hypothesis is just that something is not equal. There's just something not equal about it, but we don't know what that is. You can write it this way. People write it a bunch of different ways, right? Like, but we don't know. We're not sure where it is, you know? So basically, this is your null, but our alternative is always like there is some difference. And that's where the post hoc test, and when they use this word post hoc test, it basically means after the fact. And we got to find where the significance comes from. Where the significance, here, sorry, we don't need all this extra business. Where the significance comes from. Because we don't know, right? Like the F statistic, this value, this F stat, all it does is tells us there's a difference somewhere. And our job is just to find it. Oops. So hopefully that makes sense to everybody. Hopefully that's interesting to you. If it's not, if you're super bored, guess what? It's the last video of content, so you don't have to like listen to me struggle with these videos anymore, but I hope you found that kind of interesting. So I'm gonna get into the book. I will get rid of all of these other tabs. Um, and this was my stuff. We can actually circle back to this if you'd like. These are just other things that I've done, conferences that I spoke at, just so you could have so I could find this one that had this like little table in here so I could show it to you. So cool. Um, so here we go. We're in 11.3. We got 1 through 4, 11, 13, and 14. But let's actually read the book and do the problems, unlike we did for chapter 9, because I'm trying to stick with it. So how do we get to the problems? All right, so we go to Zoom. I mean, this is in your dashboard. And we're gonna go to, I'm glad people are getting their work done. This looks nice. I'm sure I'll be doing a lot of grading. Getting messages. Let's hope it's nothing too important. All right, late assignment. I will respond after this video. Okay, so here we go. So we're here, and I'm gonna go to my Math Lab and Mastering. I'm gonna click open my Math Lab and Mastering. And then all I'm going to do is go to eText, click Pearson eText, and I already pulled it up because I was curious what they had. So, oh, I guess I have to re-pull it up. So, that's fine. I looked at it for like a second before. I always want to kind of see it how you would see it, which is always fun. So then you can see me make mistakes and hopefully not laugh too much out of it. All right, so they put chi-square and analysis of variance together. Again, if you need more information about these, you can just find them in that reading one that I made, that reading research articles. If you go here, you'll see I have chi-square and ANOVAs. These are all the types of t-tests with examples. Here's one way ANOVA. Walk through of it by hand. Obviously, I may not be the best. Here's one to practice with. Check your work. I've got an ANOVA calculator and a Tukey calculator, and this is how you write the results. Is if you wanted to go two-way. See, notice it's not just 3 groups. It's 3 groups with a 4th predicament happening. Craziness. And I know I've got chi-square in here. And we've been looking at chi-square stuff. Why are they together? Who knows? Who knows? So if you want to see somebody else do these problems, probably better than I can, here's a chi-squared. 2 groups, but it's over a bunch of different pieces. So this is how we do chi-squared. A video of chi-squared test by hand. Watch it, if you want to watch it. Here's a step-by-step breakdown, an explanation, and the result statement. Ta-da! All right, so all that's there for you. Those videos are there. You can just watch them. All right, so let's get into it. In this section, we introduce the method of a one-way analysis of variance, or ANOVA, which is used to test 3 or more populations where the means are equal. Okay, so pretty much said that already. Your null is just what? Mean equals mean equals mean. If it was just 2 of these, guess what? If it was just 2 of them, we'd be talking t-test, right? But because we have all 3, now we're talking ANOVA. All right, so we get an F statistic. Oh man, okay. They want you to do it by technology, but I will show you one by hand, or you can watch the videos by hand. We'll see how it goes. The analysis of variance methods this chapter required an F distribution which has the following properties. Okay. There is a different F distribution for each pair of degrees of freedom for the numerator and denominator. Okay. The F distribution is not symmetric. That should be familiar. That should look like T1, right? It's skewed right. So your F is like this, and so is your T. Your T is also like that. Cannot be negative. depends on two different degrees of freedom. Why do we have two different degrees of freedom? Because we've got three groups. One is the between groups, and one is the within groups. So you have a degrees of freedom between, so your number of groups, then you have within, so like your total number of people. So if we have three, it's going to be two, and then let's say we had 100 people, it'd be 2 comma 99. So when you're writing it out, that's going to be, whoa, sorry, that was crazy. So this is going to be your between, that's your within. Your degrees of freedom. All right, I'll try not to go too fast or too far ahead of myself. All right, the value of is 1 S1 squared over S2 squared. What do they mean by that? Did they even tell you? Nope. Whatever. When testing for, to me, they're talking about the variance squared. So sorry, the standard deviation squared. So your variance of 1 over the variance of 2. They're saying that's how you get F, but they don't tell you anything else about it. So I will try my best to show you everything about it because we know these are just the variances. All right, let's keep on trucking. All right, when testing for the equality of 3 or more populations, use the method of a one-way analysis of variance. One-way ANOVA is a method of testing the equality of 3 or more population means by analyzing the sample variances. Okay, ta-da. All right, so you get 3 categories. Cool. The term treatment is used because early applications of variance involved agricultural experiments. I like that. Any history I'm about in which different plots of farmland were treated with different fertilizer seed types. Oh, well, now we know. Now we know why they first came up with this. Why did they first come up with this? They wanted to figure out how to make the most food, how to grow the best food. Guess what comes into play? Statistics. All right. Use the samples for 3 or more populations to test the claim. The population must have distributions that are approximately normal, but this is a loose one. Okay, that's fine. So the population that is far from normal, use the non-parametric test, the Kurzweil-Wallace test. I've never tried that. If it's not normal, I would just say don't use an ANOVA. It doesn't look slightly symmetric for your data. You're probably not going to get any good data from it. Populations have the same variance or standard deviation. This is loose. So most of these are loose requirements. Statistician George E.P. Box showed that as long as the sample sizes are equal or nearly equal, the largest variance can be up to 9 times the smallest, and the ANOVA will be the same. So let's thank this guy, George, and give him a shout out. George E.P. Box. There's our boy, George. Look at him, killing it. So, where's he from? Oh, he's British. Why are they always British? Much smarter than me. That's okay. Killed it. He worked for chemical industries and North Carolina State. 1 million awards, lots of publications. So this statement's pretty important. This means as long as our ends are close, right? As long as the ends are close, right? The largest variance can be up to 9 times the smallest variance. So a variance could be 9 times bigger, and the ANOVA still works. Thanks, George. I appreciate that. So if we look at mine, I'll keep referencing back my picture. So if you look at my ends, 38, 42, 37. Let's look at our variances. Well, we can look at our standard deviations, I guess. If we square these, they're all pretty close. So it's not going to change that. My ANOVA is still going to be the same. If I square these 3 numbers, they're all going to be pretty close. But they didn't have to be, just because my ends are pretty close. Ends, remember, is the total, and variance is you square the standard deviations. Okay, let's keep learning. All right, the samples are independent of each other. Yep. The different samples are categorized in only one way. All right, so let's see what we do. Use technology to attain the p-value. The ANOVA test is a right tail test because only large values cause us to reject the population of means. Form a conclusion based on the criteria of the alpha. Reject if it's less than that. Fail to reject. So if we look back at mine, we can see. We look back at mine, we can see my p-value was what? 0.012035. And that is less than 0.05, which means I could reject the null and say that there is a difference between these three groups. As the calculations are messy, they want us to use technology. Okay. Understand that small p-values lead to rejection of null. The p is null. Okay. Develop an understanding. Sweet, we get to do one. Should we do it by hand? Oh, it's so big. Damn it. Maybe we can anyway. So, it is a common belief that the larger cars are safer in crashes. Head injury criteria. Okay, so we want to see the measurement of head injuries in car crash test. We've got small, mid-sized, large. So we have 4 groups. Okay. Oh, sorry. So I'm just gonna do it. So I'll use StatCrunch and I'll just do it. There's a lot of numbers. Once they show you the formula, I'll also do this by hand. So, but for right now, I'm just gonna throw. And maybe they'll just give me this data set, so I don't have to type them in. Let's find out. So it's 11-11. Just see if it comes up. I will try some magic. Thought I downloaded this already though. So it's Triola ES, whatever, whatever. Yeah, so I don't have to re-download this thing. Is there one with these cars? Oh, that is so annoying. All right, so I don't got one with the cars. What can you do? It is what it is. So let's. I'm gonna try to just find it one more time. So they were talking about head injury, birth. Oh, these are all of them. I don't see head injury anywhere. Is there a name on this thing? Measurements of head injury, so HIC. I don't see it. All right, well, guess what? I have to type them in, but that's okay. The reason why it's annoying is because there's like 4 groups. It's going to take me a little while to type all these in. So I'm going to pull this aside. I'm going to see if they'll let me copy and paste it, but usually not. Let's see. All right, well, it's going to take me a bit, so might as well get to it. Small, mid, large, SUV, 253, 143, 124, 301, 422, 324, 258, 271, 467, 298, 315, 304. Okay, that's the first group. Let's go to midsize. 117, 121, 204, 195, 186, 178, 157, 203, 132, 212, 229, 235. All right, let's go to the large. Large, we got 249, 90, 178, 114, 183, 87, 180, 103, 154, 129, 266, 338. And finally, we have our SUV. And for our SUV, we got 121, 112, 261, 145, 198, 193, 193, 111, 276, 156, 213, and 143. All right, so that's everything. I know that was annoying, but I'm assuming we go to stat. There's got to be an ANOVA here. Beautiful, one way. Remember, two way is you could go opposite way. There'd be like an extra piece here. Something separating these groups somehow. We're just doing this one way. Here are our columns. Okay, and then if it's significant, we could do this. We should always test this homogeneity of variance. This is basically like, are all of them the same? As long as we have this test in here, it lets us do the ANOVA. That's basically just making sure all of those are the same. All right, let's see what we get. Compute this thing. Okay. So here we go. 0.0003 for your ANOVA table. Yeah, they're pretty close for this Levine's test. It looks pretty fine. But yeah, good to me. So once we have something that's significant, or F stat is 760, notice that our degrees of freedom is 3. We can account for error, and that's the total. I'm allowed to do this 2 key thing to see where the actual difference is. So let's check it out. Where's the real difference? So which one is the real difference? 0.05 was our level, right? Boom, boom, boom. So so it works for all of small. What do I mean by that? Small is different from all of them. The small cars suck at the crashes. Small is different from the mid, the large, and the SUV by a lot. And then the mid size is not different from the rest. And the large is not different from SUVs. The only real difference, what was the only real difference we found? Was that the mean of the small, this 290, was significantly different than the rest of these three. And these aren't really different from each other. Ta-da! That's the whole thing. Let's make sure we did it right. There's our null hypothesis. Our alpha is 0.05. They got a 0.0003. So did we. Our critical value is 7.68. Our critical F is 2.861. Where's that critical F? They not give us the critical value. So that would be annoying. Yeah, they don't. So they don't give you the critical value, which I already don't like. How can we find that critical value? It says the critical value is 2.81. Sure, there's a calculator for that over here. Let's shrink this guy. Stat, calculator, F. Our number of degrees of freedom for the numerator. I believe our numerator is going to be the small one, so that's going to be the between, so that's going to be 2. And our denominator is the whole one, which is going to be 47. And we want this at the what? The 0.05 level. Oh, we got to swap it around. And we got a 3.19. They got a 2.81. So let's figure out how they got this critical value. Unless the top is 3. Should it be 3? All right, let's see what they got. All right. So their degrees of freedom is 3. Oh, because there were 4 groups. Cool. So 3, and let's put this 0.05. Sorry. And we're 2.80. We're still off. Our total should be 48 minus 1, so it should be this. So I can pretend it's 44 for the error. See if that gives us the right answer. I'm just curious. Okay, so that's how they get it. So I'm always just curious to see how they actually got the values. So what is a way to find the critical value? Well, you have to take, we have 4 groups. So 4 groups minus 1 is 3. That's our degrees of freedom on top. Our denominator is just the error. So how do we get the denominator for this thing? We have to take our total, 12, 24, 36, 48. There's 48 numbers in this here. We got 48, 12 times 4. And we have to subtract 1 from each. Boom, 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 boom. That's our denominator. So we get the critical value. Because our F statistic, the 7, is all the way over here somewhere. That is more than this 2.8. We know it's significant. All right, I hope that was clear. Let's keep it going. This means, oh, they do it in Excel for us? That's nice. Let's Excel look at it so I can show you how to do it on Excel as well. Because why? Honestly, why not? Let's see if I can grab the tops too. All right, I copied it. I hit Control C. I'm going to open a new sheet. All right, it won't let me. There's just too many things here. Sorry, my allergies are going crazy. Hopefully that didn't gross you out. If it looked like I was picking my nose, cool. So let's see if we get the same values. How would I do this on Excel? I've only really used like SPSS in the past, so doing the data on here is a little weird for me. So I'm gonna click data. I'm gonna move my floating head. I'm gonna click data, data analysis. We want to do a one-way ANOVA. It's got to be here somewhere. Here's ANOVA, single factor. That's what we have. All right, so here's the input range. Here's all our data. Ta-da! We have labels in the first row. Our alpha is 0.05. Columns, beautiful, beautiful, beautiful. What's it? Okay. Beautiful. So T, F critical, still that 2.81. I love it. 0.00031. I love it. Exactly the same. 347. We're perfect. We are perfect. We have everything we need. Does it do a 2 key for us? Who knows? Let's go back one and see if it'll do this 2 key for us. Doesn't have it. Well, isn't that a shame? I've always done my 2 keys by hand, but it's kind of annoying. So let's see if we can make a 2 key HSD test on Excel just for the fun of it. All right. To perform this, ANOVA, there should be a what? There should be a checkbox. I did not see a checkbox. All right, well, I'll try one more time. Data analysis, ANOVA. Here's the data. There's some crazy options I'm not seeing. All right, well, it says you can do it here, but it doesn't give you the option to do it there. So whatever this was saying. Let's see how this guy figured it out. Data ANOVA single factor. Okay. Labels in first row. I did all that. That's exciting. Output, oh, that stays on the same one. From the ANOVA output above, you see that the p-value is 0.00, whatever theirs was. However, we do not know which group contributed to it. Sweet. So we have to group the pairs. We get the absolute positive values for each of them. So we're finding the averages of each. And so we find the average of each of these. And we calculate the standard error, which is just the square root of the means of the standard error divided by n. And here's the Tukey. Okay. Well, that is basically doing it by hand. They're basically doing this by hand and then just dragging down every step of the way. This is how the Tukey figures it out. But if you have StatCrunch, honestly, why would you even need to do it, you know? I wouldn't do it. So that's just me. So you have to make your own tables, put in these absolute differences for each of them. It's just annoying. Okay. So you can do it this way. I wouldn't recommend it. I would use StatCrunch for these or do the whole thing by hand. I wouldn't go like half computer, half by hand like this is. All right, let's keep it going. Why are you yelling at me? Cancel. Okay, cool. So I guess we're not going to really be using Excel. All right, let's keep it going. All right, so our F statistic is this. There's our p-value, interpretation, blah, blah, blah. We reject the claim, but we cannot conclude either, excuse me, until we do a Tukey, which is fine. How's the p-value related to the test statistic? They're almost the same thing, right? So F statistic and p-value, small F statistic, large p-value, fail to reject. Okay, this is interesting. The F statistic is the ratio of these two estimates. That's where it comes from. So it's the variance between over the variance within. That's what's happening. Variance between over variance within. This is like what it's actually doing. So this is important. How do we get this F? We know it's going to be that variance between over that variance within. What does this mean? Between groups and within each group. That's where it comes from. Why not just test two samples at a time? Oh God. Well, one, that'd be annoying. And two, we're not sure like if there's an interaction. Like we can't tell if there's an interaction effect when this is happening. If you're only doing two at a time, guess what? Two might be messing with four, which messes with well, three, right? So that's the difference. Like we're trying to find these main effects, but if we're just doing two at a time, we lose what's called an interaction effect. Yep, it's going to affect the significance level too. All right, let's do it by hand. Here are the calculations. Oh, table 11-12 can be helpful in understanding the methods of ANOVA in 11-12. See that data A is the same as data B. All right, so we have three samples. There's the variance between, the variance within, and we have much different F statistics and different p-values. Okay, that's cool. Calculate the variance between samples, evaluating nsx squared, where the variance of the sample means each set of samples that is considered the sample means to be an ordinary set of values to calculate the variance from the central limit theorem. Standard deviation of x, standard deviation over n. All right, so this is how they got the variance between samples, variance within samples, calculate the test. Okay, so we get to do one of these by hand, which is good. We should be able to do one of these by hands. And let's look at it. So I'm going to show you how to do one of these by hand. I'll use Excel as my guide as I do it by hand. Just so that we don't have to be really crazy. Let's just do data set. Let's do data set A. Why not? Set a data set B. So let's go to a new sheet. We got sample one, sample one, sample two, and sample three. Remember, we can do the whole thing by, you can watch the video of the whole thing by hand. This is really small, so we can do 7, 3, 6, 6, 6, 5, 6. Oh, sorry, 6, 5, 5, 8. Then we have 4, 7, 6, 7. 4, 7, 6, 7. Now, if you're going to be working with data, the best thing to do is to make a chart. So our chart, the first thing I'm going to do is just say sample. I'm just make it 1, 2, 3. That's the first thing I'm going to do. So I can have everything that I need right here. I'm going to need my n, which is my number of participants or whatever it is. I'm going to need my mean or x bar. I might as well spread these out a little bit. And we also need our variance. So I'm going to get my standard deviation, and then I'm also get my s, which s squared, which is the variance. So these are the pieces we need in order to calculate our f statistic. And remember, the f statistic is just what? And here we go. I'm going to, we have everything we need. So I'm going to go to home, make this look like an actual table. Boom. And we're going to just grade these out. All right, so here we go. I have to move this so I can actually see what I'm doing. All right, so first thing we do is need our ends for each. So ready? What is that? We have how many numbers here? You can look on the bottom, it says 4. 4, 4, 4. Now our mean. If I literally do this, it does the mean for me. Isn't that nice? 5.25. 6. And finally, 6. Cool. Now we need our standard deviation, so equals STDEV dot S. It's just a sample. Here we go. This is the first one. And then I can just drag this down for the other ones. Oh, no, it's not the same. A2 to A5, we need B2 to B5. Sometimes when you just drag it, it does what you need it to do. But sometimes it doesn't. So guess what? That's okay. And this one is going to be C2 to C5. So I just have to change this one to B. Whoa, whoa, whoa. What? Look at you being all weird. All right, so I was trying to be fancy with it, and it got all strange on me. So this is my B2 to B5. I'm just going to go equals STDEV dot S and not be fancy about it. C2 to C5. Perfect. So we've got them all. Standard deviation A2 to A5, B2 to B5, C2 to C5. You just looked at, oh, I have a minus in the front. That's not good. Standard should. Sweet. These two are exactly the same. This one has a minus in the front. They shouldn't have a minus because it's squared. So that's how I knew those were off. All right, now we need our variance. We just have to double them times itself. And finally, sweet. So we have all of our values, which is real nice. We've got everything we pretty much need. So all we have to do now is everything the same. Everything looks exactly the same as over here, except for this one. They say it's 5.5 for the mean. 7, oh, because that's a 3. Oh, man. So, ready? Might as well change this. 5.5. Ta-da! And then our standard deviation changed, and our variance is 3. Perfect. We have everything we need. So to get the variance between, so this is to get our F statistic. All we have to do is the variance between, which is what? To get this, to get our F, is just going to be what? Variance between over variance within. That's all we have to do. So to get the variance between, it's just going to be the number of terms times the variance, and that is it. The number of terms times the variance. And this one is just going to be what? When you add all of these up, and this is like kind of like your pooled variance. That's what the SP means to me. You pool the variance with it. That's what this SP stands for. SP. Okay, so how do we get those two? So to get this one, all we have to do is take our total, right? What do we have for our total? Well, all we need is your n, which is how many things we have. So there's 4. And we have to figure out this value, right? This 0.08333. Now you can think about where that comes from, right? You can think about this. It's just these means happening, right? It's between the samples. Where is this mean coming from? Maybe they actually give you a good definition of it. Between samples. The sample means and n is the size of each sample. So how does consider the sample means to be an ordinary set of values? For example, the sample means of data set A are 5.5, 6.0, and 6.0. These three have a variance of what? 0.0833. So we need the variance of each of the means themselves. So here we go. Our between variance is equals standard deviation, STDEV dot S of what? Our first mean, which is 5.5, plus our second mean, which is 6.0, plus our third mean, which is 6.0. Those are our 3 means, right? Where are they? They're literally right here. Hit enter. Oh, I guess I have to do the actual values. That's fine. I'm cool with that. So ready? Here are the values. There it is. Now that's not the value we get, because what do we have to do? This is the between variance. We need the what? The standard this is the between standard deviation. So to turn into variance, all we have to do is square it. So the between S squared is just equal to this value squared times itself. And that's how they got that 0.0833. So it's 4 times this value Then all we have to do is multiply. We put an equal sign in the front. You'll see that it is. We found a typo. No, I forgot to put the multiply sign. And that's how we get the top, which is 0.3332. The bottom is pretty easy. We just have to find the variance where? Within the samples. Do we have them all? It's called pool variance. It's basically an average of the variances. That's how I always think of it. We want an average of the variances. All we have to do is take the three variances and divide them by what? How many we have. So here it is. Equals 2. I'll do parentheses. Our first variance is what? 3. Our second variance is what? 2. Our third variance is what? 2. And all I have to do is divide that by how many do I have? 1, 2, 3. 3 groups. Ta-da. That should be the bottom. Is that the match? It is a match. So all we have to do for our F statistic is do what? We have to divide them both. So it's equal to the first value divided by the second value. Here's our F statistic. Matches right here. But that is exactly how you do a what? This is how you do a ANOVA one-way analysis of variance by hand. Now, I know that's not the craziest thing in the world. That's how we do it. Now, how do we get the p-value? Well, you can use the dreaded tables, or if we go right here, sorry. Or, as I said, if we go right here, we have this, the F calculator. So let's see if we get the right value. They say it's going to be what? They say the p-value is 0.8668. Well, we're to use the critical value to test it. I'm not sure how you got this p-value. I'm sure they'll show us, but this is our critical value. So what do we need to test it? Well, my degrees of freedom now is 2. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 minus 1, 2, 3 is what? 9. So, and we want this to be what? 0.05. We got a critical value of 0.14. It needs to be bigger than 4. Not significant. Fail to reject the null. There is no difference in the means. Ta-da! Excuse me. So that's how you do it by hand. All right, all right, all right. Did we get the same thing? They got 0.14. We got 0.14. I like it. Oh, and our F statistic is 4.25. Is that what I got? 4.26. Oh, no, it's exactly the same. So we did it right. I love it. We got them all right. Hopefully that makes sense. I think we're ready for the problems. Caution with unequal sample sizes. Well, calculations for cases with equal sample sizes. Like calculations for cases with equal sample size are somewhat reasonable. Okay, so this is if we have one that's not equal. We must weight the measures. Here we have 12 of each, worked out. Here we have 4 of each, it worked out. But you have to weight them. Identifying which means are significantly different. You can look at box plots, confidence intervals. All right, let's see what else we got. There are several formal procedures for identifying which means are significantly different. Some of the tests are called range tests, allows us to identify them. Other ones are called multiple comparison tests. Make adjustments to overcome the problem that significant level increases. So you got the Duncan test, student Newman Cools, or the Tukey test. That's the one I always use. Let's consider a Bonferroni test. Okay, so let's look at this one. I've used this one before, but I don't really remember how it works. So let's see what it does. All right, so for the Bonferroni, do a separate t-test for each pair of samples. For the estimate of the variance, we find the means and standard error. Okay, so we subtract the means and find the error. After calculating the value of the test statistic in a pair of samples, we find it. We use the critical. Okay, so after you found significance, you can do this move with a t-statistic, the means, and the mean standard error. And where do you get that mean standard error from? It always comes up. Okay, they always give it to you. See, look. See, we got the mean standard error. So guess what? We can do this using the t-test to find it, but your stats do it for you. If you want to do this by hand, more power to you. I would just use the Tukey that's in here. Every basic stat program will tell you what it does. We're just finding the difference between the means. But we can't just subtract the means. We also have to see if it's like significant, like right here. So that's why we have to add the error. You have to take the difference of the means, divide it by the square root of the standard error, then also use the different sizes of the ends. That's how the Bonferroni works. Now, a lot of these statistical programs have Bonferroni, have Tukey, have them all in there for you. So okay. Use the Bonferroni test, discuss it. Okay, so let's do, this was the first one we did. Notice that they have that mean standard error. Does it match ours, right? Does it match ours? Oh my God, it's right here. Here's the mean standard of error. 5026.3371. There's 12 in each group. Boom, boom. And we have to do this for every single mean. So these are the first two means. That's the small car, and that is the mid-size car. There should be some difference here. Because notice in our Tukey test, we found differences between small and mid, small and large, small and SUV. They're all significant. So this one should be significant. Yeah, they're all significantly different from the first one, but that's it. These don't do your Bonferroni, which is kind of annoying, to be perfectly honest. Because it doesn't do this and it shows it in the book. What am I gonna do? I'm just gonna do it real fast on Excel just so you can see it happen, especially if you don't trust the data. A lot of times I don't just straight trust the data, but because that's me, I always just want to make sure it works out. So we should already have this in Excel, right? I think I put it on this sheet, and here's our values. Cool. All we need is the mean standard error and the means for everything. So we're good to go. We can do these. So here we go. Remember, this is your formula for this Bonferroni, but remember yours does Tukey. So here it is. T is equal to mean 1 minus mean 2. Then all we have to remember to do is to divide this by the square root of the error times 1 over n1, which is your first piece, plus 1 over n2. Now, as long, like, it's kind of tricky to remember, but I'll at least show you how they got that value. It's not a big deal. So here we go. I just need a parentheses here. So this is the formula they do. But we have the values. So the first one, we're just going to do small paired to medium. How do we do that? So this is our numerator, and we're just getting the t-statistic. So our numerator is what? It's equal to the first mean minus the second mean. Oh, that's the top. The bottom is equal to what? So it's the square root of what number? Well, it's the mean standard error, which we have here. Then I need another, oops. I just need another parentheses. All right, and then I have to multiply this by, I need another parentheses here, 1 divided by 12. Okay, close that, plus 1 divided by which one? This 12. This helps us, but they're usually going to be the same value. Close. All I have to do is close this again for the square root, and I should be good to go. Oh, I need one more. That's okay. So there's our bottom. So to get this value for this Bonferroni, which is basically like just doing a two key, all I have to do is take what? This value divided by this value. And oh my God, we got the same thing, 3.775. We look at the degrees of freedom, 48 minus 4, which is 44. So we need a t-statistic. Okay, so how do we get the value for the t-statistic? I can go back to StatCrunch. Here's my calculator. The t. We have 44 degrees of freedom. We're looking at this to be 0.05. But we got to go the other way for 0.05. And I believe it's going to be a 1.68. $44. They got a t-statistic. Oh, our test statistic is 3.75. And the two-tailed p-value. Oh, we're talking two-tailed. Or 0.03. So reject null. Let's go the other way. I'm not getting the right value. The test statistic with the degrees of freedom of this and the two-tailed p-value is this. We adjust the p-value by multiplying by 6, the number of different possible pairs of samples. Okay, well, that's already really annoying. I would not be doing the spot for anything. I would just skip it if you have it. If it can't like just literally push these out for you, doing this and then multiplying by 6 is just extra effort. I would not worry about it. But at least we got what the t value was for it. Are we at the end? I had a feeling. Cool. So they didn't say chi-squared once. Are you surprised? I am not surprised. All right, let's see the problems. Okay, cool. I hope that was useful. All right, let's look at these problems. 1 through 4, 11, 13, 14. 1 through 4. All right. Oh, they gave us the answers? Oh, that's so nice. Gotta move this. All right, what do we got? What characters of the data above indicates we should use a one-way analysis of variance? We have more than two groups. So here's A. 1A, more than two groups. I might as well look at the back just to double check these. And we're doing 11-3. Eleven dot three. Okay. One in the back doesn't match unless I'm crazy. They're talking about impressions. Well, guess what? I'm not worried about it. So I'm not going to be checking them. It's because why we're using a one-way analysis of variance. It's because we only have one set of groups. The objective is to test the claim that the four have a mean. Oh, it does say chest compression. The objective is to test that the four core sizes have the same mean chest compression. Why is the method referred to as analysis of variance? The following data is chest compression. Okay, so it is different data. Okay, so they say I say because it's three groups. They say it's because it's they're all broken down by one different category. They're all being used in one way. The objective is to test the claim that four car sizes have the same mean chest compression. Why is it for to analysis of variance? It's a great question. They say it's just the method used to test it. I don't like that. You know why? What I think the answer should be. So I think it's different for A and B. That's just me. So I think to get this F stat, we are finding between versus within of variances. That is why. It's analysis of variance because that is what we do. We take all the between variances, we take all the within variances, and we do what? We divide them. We find the ratio of these two, and that's how we solve it. Let's go to two. Why not test two at a time? They say that it makes the significance lower. The sig lowers. I think the problem is you can't see main effect. The problem they're saying that if you keep doing these tests over and over again, the significance keeps falling. We have a smaller n. The significance lowers smaller n, which totally makes sense. I think the problem is whose possible interactions. So I have different answers for all of these. You pick which one makes the most sense to you. All right, let's jump to three. But I get it. With the smaller ends doing one at a time, your significance lowers. It's harder to find active results. Yeah, this looks stupid. Three, what is the value of the test statistic? In our case, the test statistic is 3.845. All right, what is four? Oh, what distribution is used with the test statistic? I don't know. What do they want for this? Oh, okay. Well, it's that, and they just say it's the F distribution. Whatever. Let's go to four. It's 1 through 4, right? Yeah. We use a 0.05 significance level with the data given. What is the p-value? Our p-value is 0.016. And our alpha level is 0.05, which we're going to do what? We're going to reject the null and say that there's a difference. There is some difference, but we have to find it. There is a significant difference in one of the means, in some of the means, in the means. You can obviously, what would I recommend you doing? I would recommend you, where's my ANOVA? I would recommend you just clicking this button and seeing how you write the result section. Here it is. A one-way ANOVA revealed that there was not a significant, that there was a statistically significant difference of chest compressions between at least two of the groups. And I'd put this here. So I might as well write this for you. I think this is the most important part. This is how it's shown in research. So here we go. And I will type it very poorly. Sorry. Over here. Okay. A one-way ANOVA. I would actually write analysis of variance. If you're ever going to use one of these, always start with what it is. Was one-way ANOVA revealed that there was a statistically significant difference in chest compressions between at least two groups. All right, so we have to do F between comma within. So that's between 4 minus 1 is 3. What's the within? Within is 44. Oh, come on, be my friend. There we go. We have to put the value. In our case, it is 3.815. And this is comma, the P is equal to 0.016. Ta-da. And this is exactly how it will be written in a research paper. Isn't that exciting? All right. Well, we did 1 through 4. Super easy, 11, 13, and 14. Here's number 11. Jeff's parent is a statistic instructor. Okay. Triathlon are his times in minutes recorded while riding a bicycle over 5 stages. Use a 0.05 to test the claim that each does one of the miles appear to have a hill. All right. I don't know what they want me to do for this, but I might as well. What do they want to do for these? We just have to do the test. Cool. And we're doing number 11. All right. So we can use StatCrunch or we can use Excel. I've been jumping back and forth. I might as well just go to StatCrunch, new data table. Cool. Oh, let's try that one more time. Control C. It really hates to copy. Oh, that's annoying. All right, so I'm just gonna do it like this. There's not many here. All right, I'll let you try the last ones yourself. Mile 1, mile 2. They just want to know if there's a difference. They don't even want me to do a Tukey. What a waste. So 315. I gotta go down, okay. 324, 323, 322, 321. Oops. 321. And then I have these. 319. Just want to see if they're different. You might be like, oh wait, they're times. Just treat them like this. If you want to convert them all into seconds by what's a good way to do this? If you feel like because of the times it messes you up, what can we do? We can multiply 3 by 60, right? 3 times 60 is 180. So what's 180 plus 15? 195, right? We can change them all into minutes. You don't like the times this way, but I don't think it's really going to matter. Just so you know. If this was my data, you know what I'd be doing? I'd be changing them all into minutes, to be perfectly honest, because this isn't out of 100. So I don't like it. I don't like it one bit, but that's okay. Let's see if they use minutes. They don't even use minutes in the back. It's so annoying. But that's okay. 317, 319. I'd be changing them all into minutes. The last one is 334, 331, 329, 331, 329. Okay, cool. So what am I gonna do? I'm gonna go to edit, stat, ANOVA, We're doing one way. We're taking all three. I'm gonna do my 2 key. I'm gonna test for variance because that's what I should be doing every time. It's significant. There's a difference here. If they want to know exactly what the difference is, where's the difference? The difference is mile 3. Mile 3 is different from mile 1, and mile 3 is different from mile 2. So what does that mean? Let me move my floating head. Our differences are right here between 3 and 1 and between 1 and 3 and between 2 and 3. So this means my only different mile is mile 3. There's probably a hill in mile 3. Ta-da. All right, so 13. How about I do 14 because you can't 13's in the back. So I'll do one more. Here's 14. Data set number 38. Let's find this thing. All right, well that sucks. And M. All right, cool. I like it. Use in appendix B, use the weights of the M&Ms, test the claim, have the same mean weight. Is the result as expected? All right, so we've got all of these. This is going to be tough because we have different values of each. So I'm definitely not doing this one by hand. I'm going to go to graph, I need stat, ANOVA, one way. I need them all. I definitely want to do the 2 key test for homogeny of means. That's fine. All right, let's see what we get. Nope, they are not different. Are you surprised? I am not surprised. They are not different. They are the same. We can't say that the means are different. 0.86, 0.85, 0.83, 0.84, 0.85, 0.86. Those means are the same. Ta-da, exactly how you want it. There was some specific difference. What we do, we'd look at the 2 keys, but nothing significant. All right, well, that was the last one. I know it was long. That's okay. I showed you a little bit of my research in there too. Or studies that I've run in the past, and I luckily got to present on back when I was doing a lot more stuff. But yeah, just reach out if you need help. Take care.